All right, let's start. Good morning. Today we're going to keep working on, or this week we're going to keep working on integral calculus. There's this theorem about characterizations of Riemann integrability, and I'm going to prove the equivalence of two statements. The rest is part of the problem set due this Friday. Somehow the remaining items are more in the sense of sort of rearranging the definition, whereas one and this fifth item, they're really sort of slightly harder to prove the equivalence of. And so we're going to do that. And then, if time permits, we're going to transition to gauge integrals. I'm going to take attendance today, too. So, as usual, I is a closed and bounded interval from lambda to rho. Here I wrote a couple of definitions that are relevant in this case. If I have a function f on my interval, something like this, right? The partition was, well, you chop this interval into finitely many pieces, let's say like this. That's your partition. You can think of the cut points or the pixels. You can do it either way. And then what was a sampling function? Sampling function was a choice of one point in each of these pixels. So maybe we can do sort of like something like this. Say this point, and then this point over here, and then let's say exactly this point. That would be a sampling function or a tag, or tagging function. And then how do you build the Riemann sum? Well, this is a finite number always. It's a sum over finitely many things. And so you look at each of these pixels in your partition. You look at the lengths of each of these. And for each pixel, you multiply the length with f of whichever point you sampled out for that specific point, for that specific pixel. Okay, something like this, for instance. And then this Riemann sum over here, we'll just color code it like this with orange. Well, it's the area of this. Okay. The notation makes things look more scary than they are. This is all that's happening. Okay. What else? Well, if f is bounded, then I don't need to, without looking at a sampling function, if I were to just choose a partition, for instance, P, well, what I can do is I can look at the inf of the function restricted to each of these pixels. So for instance, in this pixel, the inf is here, this height. For this middle pixel, the inf is something like this. Okay, and for this pixel, the inf is the same thing as this sampling point, this height. Okay, if you were to look at the area underneath, that gives you lower Darboux, and okay, so I'll just use red again. If you do the same thing, but instead of using infs of the restrictions of the function f to each pixel, if you were to use a soup, well, that's going to give you an upper bound then. And if you were to do the same thing, okay, that would give you the upper Darboux. And the difference between these two, u minus l, for the same partition, I'm denoting here by d, dfp, this is the Darboux aperture. It's the area here. the amount by which U and L differ from each other. This is D. Like I said, notation makes it look scary, more scary than it is. But this is all we're trying to do, ultimately. I'll just erase this color coding at this stage. Any comments or questions about this? This we had talked a little bit, and I realize, it's hard to sort of get accustomed to this formalism. That's why we started with step functions. Functions, as far as I'm concerned, they are easier to think about. But when you switch over to sort of these lower and upper Darboux sums, things that are functions of the partition, or sampled partition, it becomes harder to think about, I think. Yeah.
Can you repeat what par and parenthesis I mean?
Par of I, this is the collection of all partitions, finite interval partitions. So I'm imagining it like this. Okay, so say your I is 0, 1 for simplicity. Here is par of I. Somewhere here, for instance, is the partition into 1 pixel. That's a partition in and of itself. Okay, don't partition. But somewhere here is like 0, 1, 0, 1 half, 1. Somewhere here is 0, 1 half, 1 over 4, 1. Somewhere here is something more complicated. This is the set of all partitions like this.
It's not a sequence?
No, it's a set.
The way we partition.
Even then, because when we're using the word sequence, we don't mean finitely many terms. So with a partition, you're only allowed to chop into finitely many pieces. Okay? So when we say partition, we really mean finite interval partition.
And does it have to be symmetrical?
No. It doesn't need to have any symmetry, exactly. You can chop it into 1 over n, 2 over n, 3 over n, whatever. Or if you want, you can do like 1 over n, 2 over n, and then 8 over n, or 7 over n, whatever. It doesn't need to have any sort of symmetry. Okay? It's a perfectly valid thing to do. And later on, in fact, when we switch over to gauge integrals or HK integrals, we're going to sort of look into how to use different partitions in a sense. Because the idea is this. Somehow, wherever your function behaves badly, well, you want to have more control over there. So somehow imagine it like this. Imagine, of course, in modern technology, we don't really have that sort of a technology, but imagine sort of having a television screen where you get to use finer pixels if in some part of the screen more things are happening. Okay? So imagine sort of this is your television or something, and it's like there's like a background, whatever. There's a couch, all that stuff. And the couch doesn't move. So you use fewer pixels there. Nothing interesting is really happening. But maybe there's sort of some motion here. Okay? A burglar is just like moving around in the house, whatever. And so you want to sort of like use more of the resolution there where things are happening. Okay? Does that kind of make sense? This is kind of the heuristic, yeah. Of course, it's an art to, in this case, it's kind of clear, but in the case of sort of using functions and stuff like that and trying to integrate them, it's going to be part of the art to figure out where you want to use your finer pixels. Very good. So this is the set of partitions, but I can also consider the set of sampled partitions. Okay? These are both sort of distinct sets. So this is S par, this is par. The only distinction is that with par, I don't have any samplings, but if I were to also put samples here, that would be the set of all sample partitions. Okay. Okay. Now, let me give you one exercise related to this picture over here. If I were to fix a partition, P, then I get to use different sampling functions for it. Okay? Remember, for each P, we had this S of P, the collection of all sampling functions adapted to the partition. But if I were to vary only the sampling function, well, the Riemann sum is going to change quite possibly, but L and U are not going to change because they don't depend on the sampling function. Okay? And in fact, for any partition and for any sampling function adapted to it, the associated Riemann sum is going to be between L and U. Okay? Because in a sense, this is the minimum possible Riemann sum you could get, kind of. It's not the minimum possible, but the infimum possible, if you want. And likewise, this is the maximum possible. And in fact, you can approximate this using Riemann sums in the sense that this is the inf of all Riemann sums for arbitrary sampling function. LFP is the inf of all Riemann sums, where S is a sampling function adapted to P. And likewise, U is a soup. Like I said, I realize these kind of things look scary, but ultimately the way you prove these kind of things is nothing more than just opening up the definition of the inf and soup, whatever. They're essentially logical exercises. Okay, so if I have a function, so this is the theorem about the characterization of Riemann integrability. If I have a function f, then the following are equivalent. One, f is Riemann integrable, meaning its lower integral and the upper integral coincide. Two, for each epsilon, there are two step functions, sigma with an underline, sigma with an overline I wrote, such that, well, one of them is beneath f, the other one is above, and the difference between their integrals is bounded by epsilon. So for instance, the equivalence of 1 and 2 is essentially opening up the definition of the soup and inf. See? Oh, okay. 3, for any epsilon, there is a partition such that the upper and lower Darboux sums associated to this partition differ by at most epsilon. In other words, the Darboux aperture is bounded by epsilon. The equivalence of 2 and 3 is slightly harder. But ultimately, this has to do with the idea that if you have two step functions, you can synchronize them in the following sense. Say this is your thing, what you're trying to do. Say sigma with an underline is something like this. Okay, this is sigma with an underline. And then like this, like this. And say sigma with an overline is something like this. Okay, then say 0. Of course, in this case, sigma with an overline is not underneath sigma with an underline, but it doesn't matter. Given any two, maybe I should have written sigma and tau. Given any two step functions like this, okay, well, sigma, or rather the level sets of sigma, split the interval, the domain, into 1, 2, and 3 pieces. And likewise, the level sets of tau partition the domain into 3 pieces, 1, 2, and 3. Well, what I can do is I can say, well, if I were to look at this partition, the coarsest common refinement, then both sigma and tau are step functions adapted to this finer partition. So ultimately, this is what you use in showing the equivalence between 2 and 3. Okay, it's all about synchronizing the pieces on which your sigmas and taus are defined. 4, 3 and 4 are very close to each other. You can basically farm this statement to get a sequence of partitions whose Darboux apertures goes to 0. There's a sequence of partitions such that limit as n goes to infinity of the associated Darboux apertures is 0. Again, what does that mean? You have for each n one partition p sub n. To that, you associate a u, an upper bound on the integral, and an L, a lower bound. And you say, well, the function is integrable insofar as I can make the difference between upper estimate and the lower estimate arbitrarily close. 3 and 4 are both the same idea, essentially, and 2 and 1 also. 5 is the more suspicious one, and that's what we're going to prove. Hang on a minute. I want to do something here. I should also add in 3 and 4 that f is bounded. So f is bounded and. So f is bounded and. Okay. 5. This uses the idea of the mesh. There is an R star such that for any epsilon, there is a delta such that for any sampled partition, if the mesh of the partition is bounded by delta, then the Riemann sum associated to the sampled partition is within an epsilon of R star. And of course, in this case, R star is the integral, the Riemann integral. I'll write that too. there is a unique such R star, and it is equal to the Riemann integral in this case. Okay. What was the mesh? Well, you take your partition. It has a bunch of intervals in it. It's a collection of intervals. To each interval, you can associate a number, which is the length, sup minus inf. Well, mesh of the partition is the sup of that. I'll write it here. Okay. Take one pixel in your partition, look at the length, and then maximize that value as you vary over all pixels. That's the mesh. Sometimes you might see the word size of the partition or norm of the partition. I think mesh is also fairly common, so that's what I'm going to stick to. This is a statement. Okay. So like I said, the equivalents of 1, 2, 3, and 4 are in the 6th problem set that is due this Friday. Those are going to be for you. I think what I'm going to do is I'm going to prove the equivalence of 5 and 3. I find this rather convenient, this aperture control. Proof of 3 is equivalent to 5. Okay. Thinking. Let's start with 5 implies 3. It's slightly easier. Okay. So I suppose there's an R star, some real number, such that for any epsilon, there's a delta, such that for any sample partition PS, if the mesh of the partition is at most delta, then the associated Riemann sum is within an epsilon of the target R star. Okay. And I want to show that I can make the Darboux aperture as small as possible. Okay. So as usual, we start from the end, meaning we start from what we're trying to control, the aperture. That's what I'm trying to control. This guy. I'm trying to control this, and I'm given that I have some control over this. Okay, somehow I want to use these guys. So, without even worrying about epsilons, deltas, whatever, I'm just going to try to come up with some relationship between the Darboux aperture and something like this. Then, the Darboux aperture of f associated to p, well, by definition, this is u minus L. By the way, like I said, in the textbook, they don't use this notation. But as you're reading the textbook, you're going to see this expression quite a bit, u minus L. So I find it a lot more convenient to sort of package it into one thing. But when you're proving things, you end up needing to open it up, of course. OK. So here's the interesting thing here. Okay. Instead of writing it like this, what I could have said is also something like this. Instead of choosing a sampled partition here, I could have chosen just one partition here, because my hypothesis here does not depend on the sampling function, and then I could have put a soup over all s's. In fact, I'll write it here as 5 prime. These two are logically equivalent. And that is what I'm going to leverage, really. So 5 prime, I don't want to call it 6. There's an R such that for any epsilon, there is a delta such that for any partition, yes, if the mesh of P is bounded by delta, then no matter which sampling function I use, the associated Riemann sum is going to be within an epsilon of R star. These are logically equivalent, 5 and 6. That's because this hypothesis does not depend on S. So I can move it around. And so what I'm going to do is, in fact, I'm going to choose 2 sampling functions associated to the same partition. Say S and T be 2 sampling functions associated to the same partition. Okay, I have this. I know that if I were to look at any one of these Riemann sums associated to S or T, well, that Riemann sum is going to be bounded from above by U, and itself is going to be an upper bound on L. So I'm just going to inject those. Okay? But when I subtract a term, I need to add the same term so that things are equal. Okay. Now I'm going to subtract one target and add the same target so that things don't change. Then subtract Riemann sum associated to the other sampling function and then add so that things don't change. And then I have that. I just added and subtracted the same terms. Okay? But why do we always do this in this class? Well, that's so that we can do triangular inequality, right? Meaning, if I were to replace this number by its absolute value, that would increase, and then I would distribute the absolute values, that would increase even further. Meaning, I would have this. So 1. Okay, second term. The third term, Riemann sum with T minus R star. Then last term. Minus L. Triangular inequality. I had this number. I replaced it by its absolute value. That now is a possibly larger number. And then I distributed the absolute values. That's possibly an even larger number now by the triangular inequality. This is the one trick we use. Okay. Remember, that's why essentially we define metric spaces. I told you triangular inequality is pretty much the main source of inequalities in this class. Okay. Now, based on 5 prime, what I can do is I can replace these two by this expression. So I have twice this, and then I have this, and then that. So this is, upper bounded by twice the sup over all sampling functions adapted to p of this plus the difference between u minus r and difference between r minus l for these two specific sampling functions. And maybe I can just change this sampling function as well. St, let's say u. So minus this plus the other one. Okay. So what did we show so far? For any partition and for any two sampling functions adapted to it, the Darboux aperture of the partition is upper bounded by this expression. Okay. What I can do further is I can take the inf of this expression over all sampling functions, and likewise this, and get an even better upper bound. I'll erase this. For any partition, the Darboux aperture of that partition is upper bounded by twice this, plus the inf of this over all sampling functions, and plus the inf of all these. So twice sup over u's minus r star plus inf over all s's FPS plus all inf over all t's okay, but what is the inf of this expression? As I'm varying the sampling function, I can approximate this upper Darboux sum arbitrarily closely, which means that I can make this distance arbitrarily small, which means that this inf is 0, and so is this, which means this is nothing but twice the sup over all sampling functions of this. So that we have this expression, this bound. For any P partition, the Darboux aperture is upper bounded by twice this expression as you vary the sampling function over the same partition. And in fact, instead of u there, I'd rather use s for sampling function. Like so. That's what we proved so far. Any comments about this? Yeah.
Is it U or N?
U.
What does it mean?
It's some sampling function. I had two sampling functions, S and T. Right. I just didn't want to use the same letter. S, T, U. The next one.
Oh, another sampling function.
Yes. Well, I mean, I already had S and T in this expression, so that's why I didn't want to use the same thing. It's a different one. So this, so the S is fixed here. But if I were to compare it to the sup of the same expression as S is arbitrary, I would upper bound this by this expression. And likewise this. For one sampling function, I have this expression. But if I were to keep the T varied and allow looking at the sup, this would be upper bounded by the sup.
So from this line, the right line, the left-hand side, you are looking at one partition?
Exactly. It's always the same partition.
And on the right-hand side, are you looking at all?
Well, it's the same partition still. What I'm trying to say is that this thing works for any partition.
Partition is a way of making
Yes.
short intervals,
Yes.
right?
Yes.
Why is this abridged into just one? You have three items, 2, inf, s, inf, t, right?
Yes, because, OK, so by the end of this, I have that for any partition and for any two sampling functions, this, that doesn't depend on the sampling functions, OK, is upper bounded by this expression.
Yes.
So that means that this is an upper bound for this no matter what S and T are. So I optimize over all such bounds, which means I'm just taking the inf of this over all S's and inf of this over all T's.
And then on the right-hand side, you just abridged into one.
Yes,
That is all true.
because this is 0. So this U is the sup of all of these as S varies. OK? And so if I were to look at the distance between U for the same partition and some Riemann sum with the same partition, by changing the sampling function, I can make this difference arbitrarily small. In other words, this inf is 0.
You change the sampling.
Exactly. Yes. So the partition is fixed, but which point I choose in each pixel, I'm varying. Yes. And I do the same thing here. So this is 0, which means I don't need to write it, which means that the Darboux aperture is upper bounded by exactly this. OK? Which ultimately means we have this inequality. OK? And I didn't even use epsilons and deltas so far. But you see, I'd rather use something like this as opposed to sort of trying to move epsilons around, because now I have something that is rather nice to control. If I have 5 for any epsilon, there is a delta such that for any partition, if the mesh is at most delta, then this expression is, I can choose it to be bounded by epsilon over 2. OK? So that's how it goes. I'll do it here. So let epsilon be positive. By hypothesis, there is a delta such that for any p, if the mesh is bounded by delta, then this expression, instead of epsilon, I'm going to use epsilon over 2. Then sup over all s's of the associated Riemann sum, or rather the distance between the Riemann sum and r star, is bounded by epsilon over 2, which means that by this, for this partition, the Darboux aperture would be bounded by epsilon. And for any such p, the Darboux aperture would be bounded by epsilon by the master inequality, star. And this ends the proof of 5 implies 3. So ultimately what this showed is that if I have this item 5 for partitions whose meshes are sufficiently small, I have some stability of the Riemann sums. Well, that means that for any such partition, the associated Darboux aperture too is stable. That's what this showed. But you see, like, I haven't used any epsilons until the very end. I start from the end. I start from what I try to control. And I'm trying to control it in terms of something I know I can control. I assumed 5. I said, oh, I can control this expression. And I said, I'm trying to control this expression. And I'm sort of trying to control this using an expression of this form. That's ultimately what I was trying to do, which I was able to succeed. Yeah.
How do you go from the triangular inequality? You've got the upper bound minus Riemann on that second to last panel to your right.
This?
Yeah. How do you go from those steps to the inf? Like,
Oh.
those would be infs.
Because, so for any p and for any st, this is upper bounded by this. What I'm saying here is that the left-hand side doesn't depend on s nor t, which means that if you have an inequality like this, if one side doesn't depend on some stuff, you can optimize the other side. And so I take the inf of this expression as s varies. And likewise, inf of this expression as t varies. Okay. In other words, if you want, what you can do is this. You can look at this number, so fixed p, look at this number as str varying over the sampling functions. This is a set of real numbers, okay? It is bounded from below by this, which means by the completeness axiom, its inf exists and is, it cannot be lesser than that. You can think of it that way too. Does that kind of make sense? Yeah. It's all like completeness axiom ultimately. These are all real numbers. I'm looking at sets of numbers and optimize from below, from above, whatever. Yes.
So this st in s
Of p.
parentheses p
Yes.
is a sampling function?
Yeah, this is the set of all sampling functions adapted to p.
And why do you say it's a real number?
This set is a set of real numbers. This is a number. This is a number. This is a number. When I add them up, it's a number. It's a real number. Which means, as I vary s and t, this expression cuts out for me a set of real numbers, which I know by all this stuff is bounded from below. Which means it has an inf, and that inf upper bounds this. That's what I used here. Any other comments or questions? This is the one side, okay? I realize this is hard to parse, and that's why we're doing it in class, okay? I guarantee you the equivalence of these to this is not as complicated as this proof. And I told you, like, thinking about partitions and sampling functions, it takes a while to get accustomed to. Okay, so this is the one part. I want to do it the other way around now. I want to show if I imply 3, if I assume 3, I can prove 5. Probably not going to be able to finish it, but at least I'll start. Okay, proof of 3 implies 5. Again, I'm not going for epsilons. I start from the end. Okay? Now I start with something like this. And I'm going to try to prove, I'm going to try to upper bound it using something of this form. Now this is trickier to actually rearrange things to get get an inequality like this. Let me think. I have 5. I want to show 3. Oh, wait. It's the other way around. I'm assuming 3. I'm trying to show 5. The other way around, we already did it. OK. That's the harder part, yes. This is the harder part. So let's start like this. First, I'm trying to establish some relationship between these two. Okay? Let P be a partition and S be a sampling function. This is upper bounded by this, and it is lower bounded by this other thing. And furthermore, I'm going to pick R star to be the integral. Okay? So it's also the case that R star, which is the Riemann integral, is again lower bounded by this and upper bounded by that. Okay? If I were to put minuses, now this would be U, and this would be minus L. Because when you put minuses, you flip the order of the inequalities. Adding everything up, I have minus the aperture, lower bounds, the difference between these two, and plus the aperture, upper bounds it. I just added. Well, if you have an expression that is upper bounded by some number and lower bounded by minus the same number, that's the same thing as saying that the absolute value of this number is upper bounded by that other thing. That's a D. Okay, so this is promising, you see. For any partition, the Darboux aperture dominates this thing I'm trying to control. Now we need to do something about it, because somehow we need to be able to say, oh, if the mesh is small enough, there's an upper bound. So somehow we need to somehow control this Darboux aperture using only control on the mesh. Okay? Now that is slightly trickier, but I'm out of time for today, so we're going to continue tomorrow. Thank you. Okay, let's start. Good morning. So today we're going to keep working on this theorem. We're slightly behind schedule, but I don't mind cutting some of the topics that I had planned to discuss. I think this is a complicated enough theorem. Even the statement of it is complicated. I think it'll help you to develop some more mathematical literacy, and the proof of it too. Ultimately, the tools are rather elementary in the sense that we're only using inf and sup. But of course, when you have multiple infs and sups sort of like acting on each other, things get more complicated to keep track of. And if you're feeling lost a little bit about all this stuff, that is perfectly normal, okay? This stuff is really complicated. I mean, it takes time to get used to. Part of it is that all of these symbols, the Darboux aperture, Riemann sum, Riemann integrability, all these things, partition sets, or set of all simple partitions, mesh, you see all these things, these are all sort of like concepts that just like compress a lot of information. So it takes a while to get used to this. That is perfectly normal, okay? And this is essentially one of the reasons why, when you're taking calculus for the first time, people kind of talk vaguely about what Riemann integration is, and they don't discuss too much. That's part of the reason. If you try to formalize it, things get really nasty, okay? And as I'm preparing the class too, it's like, compared to something like continuity, it's like preparing these classes are a lot harder. It takes me a while to get accustomed to the proofs and so on. I end up needing to sort of think a little bit more than usual. So everything is perfectly natural if you're having trouble and so on. One suggestion I could make is, well, if you're trying to understand one of these things, the best thing is to just unpack the definitions, pack them back again, unpack again, pack again, and so on. Okay? That's, in a sense, the best way. And if you would like to discuss certain examples and so on, I would be more than happy to meet with you and so on. Okay, so as usual, integral calculus, the natural habitat is a closed and bounded interval for us, lambda to rho. And this theorem is about characterizations of Riemann integrability. And so we start with a function, f, arbitrary function defined on the interval taking real values. And it says the following are equivalent. Remember, I told you this is one of those rather common abbreviations. Why would we even think about something like this once we have a definition and we did define what it means for a function to be Riemann integrable? Well, this is one of those paradoxes of math. Somehow, often it is the case that defining something, a property, using method A, say, ends up being a lot less convenient when it comes to actual calculations. So for instance, in practice, I almost never use this step function approximation that we use to define Riemann integrability. For me, item 3, in fact, is the most convenient one. Okay? You might find item 2 more convenient in this context, item 4 whatever, or maybe item 5. And so depending on the context, it might be more beneficial to use different characterizations of the same idea. And in a previous problem set 2, for instance, you saw different characterizations of what it means for a function to be continuous at a point. There was a characterization with epsilon delta. We discussed a characterization with sequences. Then there was a characterization with oscillation and so on. These are all sort of like end up being useful in different contexts. In this specific case, for instance, even though this ends up being a lot more convenient in my honest opinion, 5 and 6, or 5 and 5 prime, are closer to the definition of Riemann integrability that Calc 1 classes typically refer to. You have this Riemann sum, and it's sort of like in the limit somehow approaches to something. Okay. So in the problem set 2, this Friday, I am giving you as an exercise the equivalents of 1, 2, 3, 4. These are rather of a similar type. So these are like one type of definition. And 5 and 5 prime are slightly different. So the switch between this part and this part is slightly harder. And 5 and 5 prime, it's basically a logical exercise to switch between. OK? What else do I want to say? Let me think. Oh, the other thing too, last time I taught this class, I gave this whole theorem as a problem in a problem set. And then there was a lot of issues with 5, and that's why I thought it would be better to do this in class. It is really harder compared to the other ones. So here are a couple of exercises. Well, let's first look at this. In item 5, I'm saying there is some R star target, okay, such that for any epsilon there is a delta with a property that for any sampled partition PS, if the mesh of the partition is bounded by delta, then the associated Riemann sum is within an epsilon of the target R star. That's what 5 says. Well, in fact, if you have 5, you automatically have that there can be only one R star like this. So if you have 5, in fact, you can put here a bang representing there's a unique. Okay, that's an exercise for you. And in this problem set that is due this Friday, you're also working on these ideas of directed sets and nets. While not absolutely necessary, in a sense, you might find it useful because, well, even though all of these conditions kind of look different from each other, underneath the hood, they're all using the same idea of net convergence. So for instance, for 3, okay, I want to think of d of f comma p as a function of p, as a function of the partition, okay? And so I can, if I think of it like that, I can write it like this. 3 is equivalent to f being bounded, and for any epsilon, there's one partition, p star, such that for any partition that defines it, which you're going to see this idea in problem set 6, the Darboux aperture is bounded by epsilon. Now let's read this by thinking of partitions as times. All I'm saying is that for any epsilon, there's a time p star such that for any time after p star, the Darboux aperture is bounded by epsilon. Okay, so this is like in full analogy with sequence convergence. And you can just write this by saying, or you can just abbreviate this by just saying f is bounded and d of f comma bullet, okay, bullet notation, going from this directed set. You're going to prove that this is a directed set in the problem set due this Friday, which is always a non-negative number. Well, all you're saying is that this Darboux aperture net converges to 0. That's all you're saying. Okay, underneath the hood, it's like there's a bunch of things, but ultimately this is what you end up saying. Okay, and likewise, you can rephrase item 5 with the mesh merely by saying R of f semicolon bullet notation, going from the set of sampled partitions directed with this mesh relation, okay, going into R, converges to R star. That's all you're saying in 5 as a net. Okay, so this idea of a net, somehow, some people find it more convenient. Some people don't find it that convenient. I sort of, depending on the day, I like it or don't like it. But at the very least, it could help you sort of import some of the intuition that you've developed regarding sequence convergence. Okay? And likewise, you could write 5 prime in terms of net convergence for some net of the form, well, for some net that is parameterized by the set of partitions directed by the mesh relation. Okay. This is some commentary. Any comments or questions about the statement so far? We still have some work to do, but I wanted to give an overview. So our target was somehow relating essentially the left board to the middle board. Okay. And last time what we did was, so we're really looking into 3 and 5, which I use interchangeably with 5 prime. But last time what we did was, we took our function, we supposed 5 holds, and then we derived a master inequality. Namely, we were able to upper bound the Darboux aperture of some arbitrary partition in terms of these distances, or these distances over here. And then based on that, we did some epsilon delta to get the bound we want. What we also need to do at this stage is we also need to show, in fact, f is bounded. I forgot that last time. So the proof of 5 implies 3 is still not complete. We should do that. And then we're going to prove 3 implies 5. And just to talk a little bit about this. Here, I do need to add as an additional hypothesis that f is bounded. Okay? So when you're trying to prove the following are equivalent type statements, it's kind of confusing logically speaking, because if I assume only 5, okay, initially my function is an arbitrary function. So just this by itself explicitly does not state that f is bounded. And without this statement, this is not quite well defined, because if f is not bounded, this Darboux aperture might end up taking values like infinity minus infinity. And that's why when I'm defining upper Darboux or lower Darboux or Darboux aperture, I'm always taking f to be a bounded function. This is not to say that Riemann integrable functions are not bounded, right? That was something that we proved separately. But that's a different definition of Riemann integrability that we're using. And before verifying the validity of this theorem, we cannot just say 5 implies automatically that f is bounded. Not at this stage. Okay? So that is something we need to prove also. Okay. Proof of 5 implies 3. Write it like this. Last time we did this net convergence statements. So let me put it this way. Technically speaking, even though, assuming 5, we proved this for epsilon, there's a partition such that the Darboux aperture is bounded by epsilon statement, technically, in order for this to even make sense, we first need to prove that f is bounded. So technically, we should have proved that f is bounded before even looking at Darboux sums. Otherwise, things are not quite well defined. So what we should say, supposing f is bounded, we proved last time that this converges to 0. Okay? Just using, I'm just thinking of this as a sequence, right? Sequence is pretty much the same thing as a net, whatever. It converges to 0. This epsilon delta or epsilon p statement is literally saying that. And this is something that you'll see quite often as well. You know, here, it's almost like I'm taking a logical loan. I haven't proved that f is bounded, but I'm saying, let's put that aside. Let's say that that is given to us. Assuming that, let's march on. And then we're going to go back and pay our debt. Okay? So now I need to show that f is bounded. So it suffices to show that f is bounded. Okay? So here's one way to do it. There are multiple ways. I'm going to assume otherwise, and I'm going to try to come up with a contradiction. All I know is 5. Say otherwise. Say f is unbounded. Well, if f is unbounded, if I were to take any partition P and look at the restriction of f to each of the pixels in the partition, at least one of these restrictions have to be unbounded, because otherwise f would be bounded. And for any p in par, there is a p0. There is at least one pixel such that the restriction of f to that pixel itself is unbounded. Okay. I have 5 as an assumption. So for some real number r star, let's choose epsilon to be 1. Okay, there is a delta such that for any ps, if the mesh is bounded by delta, then the Riemann sum differs from r star by 1. So by hypothesis 5, there is a delta such that for any ps in S par, if the mesh of P, what was the definition of this? P, curly P, is a collection of intervals, finitely many. To each interval, you look at the length. You take the sup of all such lengths. So this is the mesh. I'm saying P is a partition such that each of its pixels is at most, or each of its pixels has length bounded by delta. Implies that the associated Riemann sum is within one of the target, r star. R star is fixed. Okay. Let's let one partition P to have mesh at most delta. There are certainly partitions like this. I can just take the uniform partition if I want. Okay. Let P be such that its mesh is bounded by delta. And I'll leave it as an exercise to think about the fact that there are partitions like this. There are such partitions. Okay. I don't need a specific partition. All I need is one. So I'm not going to worry about exactly writing it down. Okay. Now, once I fix my partition, you see, no matter what sampling function I choose on P, the associated Riemann sum is always going to be within R star, within one distance from R star. And for any sampling function This was a set of all sampling functions adapted to P. So for each pixel, S associates one number, one point in that pixel P. In fact, let me do it this way. I'm going to take two different sampling functions, S and T. As usual, our main weapon is the triangular inequality. So I'm going to compare the distance between two Riemann sums. Same partition, different sampling functions. Okay? If I inject R star into this, right? So this is Ti like this minus R star in absolute value plus R of F comma P comma T minus R star again. But by hypothesis, both of these are bounded by 1, which means that this is bounded by 2. Okay? Meaning, if I fix a partition whose mesh is bounded by delta, then no matter which sampling functions I choose, the associated Riemann sums cannot be more than 2 apart from each other. Okay? I could have chosen this one to be a lesser number, but this is going to be enough. Now, we chose our partition P by this. For that P, there's at least one pixel P0 such that on it F is unbounded. Okay. So I'll just draw a picture here. Okay. I'm not going to draw the graph of F, but let's just do it this way. There's a bunch of pixels here. I don't want to worry about anything else, except this pixel on which I know F is unbounded. Maybe I'll do it this way. So there's one pixel, let's say, this is P0, the sort of exceptional pixel, the pixel on which bad things happen. Okay? F is unbounded on this. Elsewhere, it might still be unbounded, but I don't know about it. I'm guaranteed at least one, though. And both S and T are sampling functions adapted to P. So what I'm going to do is this. I'm going to choose one sampling function, S, and the other one I'm going to choose in such a way that it samples the exact same points as S for pixels other than this bad pixel. Okay? And then the sampling that T does for P0, I'm going to rearrange so that maybe it's going to be somewhere here, so that these two differ more than 2. And for that, I'm going to use the fact that on P0, F is unbounded. So I'm going to engineer, given S, some T, such that T is sampled so that the difference is very large. That's the idea. Okay. Fix a sampling function. Define a new sampling function like this. So T goes from the partition into the interval. It sends a typical pixel to S of P. So it samples the exact same point as those points sampled by S, except when P is P0. So P goes to S of P if P is not P0, and I'm going to use some value here. Let's say alpha if P is P0. Okay, I'm going to engineer this alpha. So right now I'm saying this alpha is some point in P0. This is alpha. Okay. So if I were to look at a partition like this, or rather sampling function like this, I have two sampling functions that differ exactly for the samples sampled for this bad pixel P0. And I want to look at the difference between the associated Riemann sums. Well, in this case, most things are going to cancel out because I'm literally sampling the same points, except for P0. Okay. See, at this point, I don't really worry about what that alpha is. I'm going to engineer that later. I'm going to continue from here. I look at this. What is the difference between the two Riemann sums? Let's do this once, opening these up. Sum over all pixels, f of s of p times the length of p, this is this Riemann sum, minus f of t of p times the length of p, all in absolute value. Of course, you can consolidate, and then I say, unless p is p0, well, this term is going to cancel out with this term, which means that this is nothing but f of s of p0 minus f of alpha. Times the length of P0. Okay? These two sampling functions, okay, differ only for this bad pixel, which means that the contributions coming from other pixels are going to cancel each other out. So the difference between the two Riemann sums could only be coming from the difference coming from this P0. That's literally what that says. Okay. And of course, I'm given that this is bounded by 2. I'll write that true. Orange dagger. So this is equal to this, which is upper bounded by 2 by orange dagger. Okay. Now, since I'm assuming that f is unbounded on P0, well, P0 has to have positive length, which means alpha could be distinct from S of P. In any event, this length is positive. Meaning, sending it to the other side, which I can do at this stage. This is bounded by some number that is finite. Okay. But you see, this says that f of alpha is upper bounded by this plus that. Right, so open up the absolute values, rearrange. F of alpha is upper bounded by 2 divided by the length of p0 plus whatever this is, which is a finite number though. But everything so far works just the same no matter no matter what this alpha is, insofar as alpha varies within p0. Meaning, this tells me that f has to be bounded on p0, a contradiction. And so that means if we came up with a contradiction, that means we assume something that cannot be the case. In other words, f has to be bounded. And this ends the proof of phi implies 3. I find it very convenient to always draw pictures like this, because somehow the symbolism is rather daunting. So, assuming 5, this statement with the mesh, we were able to prove both that f is bounded, and consequently, all that stuff that we did last time is perfectly valid. And furthermore, the Darboux aperture as a net converges to 0, which is the content of item 3. So we're done with 5 implies 3. Okay. Yes?
Can you repeat the last one, the symbol, 2 over p at p0?
No, 2 over L of p0.
Oh,
So at this stage, I said, I just said it out loud. L of p0 has to be positive. It cannot be 0. Therefore, I can send it to the other side to come up with so that I can come up with an upper bound for this expression. Yeah. And since ultimately I started with something that is the absolute value of some number, and since this is positive, I know that this is positive as well. So it cannot be negative. So I can just, instead of parentheses, I can write absolute values here. Because positive number times some number I'm saying is non-negative. Well, that means the other number has to be non-negative also. Okay? So this is the one side. Now we need to go the other way around. And surprisingly, the other way around is even harder. Okay? 3 implies 5. And really what I'm showing is 3 implies 5, assuming 1 is equivalent to 3. Proof of 3 implies 5, assuming 1 is equivalent to 3. Why would I want to do that? Because if you look at 3, it doesn't say anything about the target integral. But for 5, I need a target. And so how would you get a target from 3? Well, you would first prove it is equivalent to 1, which then gives you 1 Riemann integral. That Riemann integral would be r star, and then we would take it from there. That's why I need to assume technically 1 is equivalent to 3, or something. So put r star to be the Riemann integral. This is a well-defined real number because we're assuming 1 implies 3 and vice versa. we have this. Since we're assuming we have 1 and 3 are equivalent. Okay, so I have my targets. Okay, I need to do this epsilon delta thing now. For any epsilon, there's a delta such that for any p, if the mesh of the p is bounded by delta, I want to say that the associated Riemann sum for any sampling function is within an epsilon of r star, of this target. And I also have this Darboux aperture converging to 0. That's the content of 3. Okay. Last time what we did was this. We showed by just opening things up and so on, for any partition, I'll write it like this. And for any s sampling function adapted to p, the difference between the Riemann sum and the target r star is bounded by the aperture of p. You have this. So somehow the issue is this, okay? If we have 3, for any epsilon, we can engineer some partition such that the Darboux aperture is within an epsilon. But for 5, we need to make sure that, so we need to somehow come up with a relationship between meshes being small and Riemann sums being close to the r star. So somehow I need to really bound this in terms of mesh. That's the complicated part. So I thought about this, and again, once I know what I need to bound with respect to, or using what, I sort of moved things around a little bit, and I came up with an inequality again. Let's take that for granted. I'm going to write it in a second. And then assuming that we have that master inequality, let's finish the proof, and then we'll do this technical inequality. So I'll separate it as a lemma. Okay. This is the key master inequality. I'll write it here. Okay, goes like this. It relates, in fact, Darboux apertures of 2 different partitions. For any P and Q, okay, the difference between the Darboux apertures is upper bounded by twice the diameter of the image of F times number of pixels in Q times mesh of P. Okay. Don't worry about how this comes about. We're going to discuss it later. Let's, for now, take it for granted. And when you see expressions like this, you should not sort of try to literally read it out, okay? You should try to sort of see what this inequality gives you in terms of control. It tells you that instead of looking at the Darboux aperture of one partition, sending this other Darboux aperture to the other side, well, you have an upper bound. And the other things, you see, you have one factor coming from how much f oscillates. Okay, that's the diameter of the image. Number of pixels in Q, even though this is, of course, important, or it's valuable to keep in mind, ultimately it's a finite number. Doesn't matter that much. What really matters is that ultimately I have an upper bound on the Darboux aperture in terms of this mesh. Up to things, okay? So let's first assume this, and then keep on. And so taking this to the other side, I have this. Connecting it with this. Okay, this is upper bounded by 2 times the diameter of the image of f times the number of pixels in Q. Yes, okay. Times the mesh of P plus the Darboux aperture of Q. For any P and S and for any Q, I have this. Okay. Now, so this we have for any P, for any Q, and any S. So I have freedom there. And I'll continue from here. Remember, for 3 implies 5, this is what I'm trying to control. And ultimately, I want to control it in terms of meshes. And I have some control over Darboux apertures. So ultimately, I'm going to say for any epsilon, there's a delta, such that for any p, if the mesh is bounded by delta, then this is bounded by epsilon. If I want to bound this by epsilon, what I can do is I can bound this by epsilon. In order to bound this by epsilon, what I can do is I can bound this by epsilon over 2 and this by epsilon over 2. OK, that's what I'm going to do. OK. By 3, there is some Q such that the Darboux aperture of it is bounded by epsilon over 2. There is some partition such that its Darboux aperture is bounded by epsilon over 2. Q is a partition. It has at least one element. This could be technically 0, but I can replace it by diameter of image of f plus 1 to make it for sure a positive number. If I want this to be bounded by epsilon over 2, well, mesh of P has to be epsilon bounded by epsilon over 2 divided by this number. Put delta to be epsilon over 2 times that expression. 2 times diam of m of f plus 1 times the number of pixels in Q. That's a positive number. OK. Then, for any P, or for any PS, and any sampling function, by and so I'll just put 1 dagger, 2 dagger, and 3 dagger by daggers. Right, combining everything. the Riemann sum associated to PS minus R star in absolute value, so the distance between them, is bounded by, well, when I do this multiplication, this is going to be bounded by epsilon over 2, and so is this, so that that, or rather this, is going to be bounded by epsilon. Which is what I wanted. Okay. Yes?
Can you tell me delta? Which, yeah, you said delta as that.
Define delta to be this. Given epsilon, define delta to be this number.
And delta is what?
This number.
Yeah, I know, but distance between someone?
What I was trying to prove is, for any epsilon, there is a delta, such that for any partition, if the mesh of the partition is bounded by delta, then the associated Riemann sum is bounded by epsilon.
So delta is the mesh.
Yeah, it's the upper bound on the mesh, yes.
Upper bound.
So what I'm saying is, if my partition has mesh bounded by this number, then I'm guaranteed that the associated Riemann sum is going to be at most epsilon apart from R star, which is what I wanted. Okay. Technical proof. It's not easy. And we're not even done. See that? We need to prove that lemma. Any comments before I go into this? So, we have a loan, okay? We need to verify this. Assuming we have that, we have 3 implies 5. So you see, mathematical literature is quite nonlinear in a sense. Initially, we try to be sort of linear, first this, and then that, and then this other thing. But typically, what ends up happening is, let me take a couple loans, and then I'll pay them later, and then let's move on, whatever. And then often what ends up happening, in fact, people forget that they have loans. They don't pay their loans. So there's a lot of like statements that are left behind. Let's try to start unpacking this. We'll continue tomorrow. Proof of the master inequality. And typically, too, in literature, you would often see sort of, grandiose theorems, like this characterization of Riemann integrals. But somewhere in there would be this, bizarre-looking lemma. There would be like technical lemmas. Often people would sort of split these technical matters to the side, because if you have sort of only so much time, maybe you don't want to get into the technicals. You would sort of, separate the technical matters for those who are really interested in the, gnarly details. Okay. I'm going to start with one of these. One Darboux aperture, and I'm going to try to do something. Okay? And in fact, here is where I'm going to use this idea of the coarsest common refinement. Okay? This is U upper Darboux minus lower Darboux by definition. Now I'm going to subtract and add U and L for P product Q. I'm running out of time, so I don't want to push it. We're going to continue doing the proof of this tomorrow. Thank you. All right, let's start. Good morning. So today, finally, we're going to finish the proof of the part of this characterizations of Riemann integrability that we were discussing. The one item that I want to talk about is this master inequality that we used yesterday. It's kind of technical. Then once we're done with this, we're going to finally transition to gauge integrals, or in other words, Henstock-Kurzweil integrals. Wanted to mention something about the change in, so it's a change in plans. If you look at the tentative schedule, we're at the end, or we're in the middle of week 8, and next week we're supposed to start differential calculus. So, but we ended up covering, so we're going to be covering only the contents of week 6 according to the syllabus. So I think what's going to happen is next week we're going to start differential calculus, but I'm going to probably just drop the topics I had listed on the syllabus for week 7 and 8. So there's a bunch of like theorems and stuff from the Fonda notes. Probably we're not going to discuss those because we ended up sort of spending more time on sort of more on foundational aspects. I think that's going to be better, and I'd rather transition to differential calculus. By the end of this week, you're going to get a sense of the taste of the gauge integrals, these more complicated integrals, but we're not going to develop more advanced aspects of it in a sense. Okay, so as usual, I is a closed and bounded interval. The lemma that I used, the master inequality yesterday was this: if I have a bounded function, remember we were trying to assume that we have this Darboux aperture net converging to 0, and from that we were trying to prove the mesh definition for Riemann integrability, or characterization of Riemann integrability. But in item 3, we could assume that f is bounded, so that is fine. The master inequality says for any bounded function f and for any two partitions p and q, well, the difference between the relative Darboux apertures, or respective Darboux apertures, is bounded by this expression. Twice something that depends on the function that you're trying to integrate, number of pixels in one partition times the mesh of the other partition. Okay? And remember yesterday, assuming that we have this, we were able to show 3 implies 5, so we need to prove this now. And just to remind you what this diameter was, diameter of any set is defined like so. In this case, I'm looking at the image of f. Certainly, it's a subset of the reals. All you need to do is, well, you need to take 2 arbitrary points in this image, look at their difference, or rather their distance, look at the distance between them, and then take the soup over all such expressions. And just to sort of connect it to some other thing that we saw in a previous problem set, remember this was the oscillation of a function at a point x star. In a sense, it's very similar. As you see, I take first a positive delta, and then I look at the interval centered at x star with length 2 delta. I take 2 points here, arbitrary, look at their images, and I consequently look at the distance between these 2 points. Then I supremize, and then that gives me essentially the diameter of the image of this interval under f. Then I take delta to 0, and that gives me this oscillation. So somehow these two are very related ideas. And in certain contexts, for instance, the Darboux aperture itself is called the oscillation, or the variation of the function relative to this partition, and so on. Okay, so how do we do it? Well, I'm just going to start with this, and I'm going to try to upper bound it by something else. And I'm just going to inject this, essentially I'm going to inject upper and lower Darboux sums relative to the coarsest common refinements of P and Q. Just to remind you, this was yet another partition. Let's write it in red. So I'm going to use this P product Q. If I have 2 partitions, I can basically shuffle their cut points to get yet another partition. So this is the partition whose terms, whose pixels are of the form P intersection Q. if you want to be formal, where P comes from curly P, Q comes from curly Q. Coarsest common refinement is the name of this. I think in Taylor, they just call it the common refinement, but if you want to be more accurate, you want to call this the coarsest common refinement. There are other common refinements of P and Q. Okay, so start with this. Okay, this is, by definition, upper Darboux minus lower Darboux of the same partition. Now I'm going to inject a bunch of terms, uppers and lowers, coming from this coarsest common. So this minus this, I subtracted upper Darboux relative to the coarsest common refinement, so I need to add the same term. Subtract lower for the coarsest common. Add the same term. And finally, I have this guy. Okay. Now, in the middle, I have the Darboux sum associated to the coarsest common. Okay, I can collect it like that. And I have this guy and this guy. These I need to do something about. So I'll write it like this. This is one thing I'm going to do something about. There's a similar thing with the lowers. This I'm going to do something about. And finally, I have d of f relative to the coarsest common. Just rearrange the terms. Now, here's something to think a little bit about. I can upper bound this by the Darboux sum associated to Q. Okay, this is upper bounded by d of f comma q. I'll write it here. So first term plus second term q. Question? So, this is somewhat confusing perhaps. So, when you see something confusing, that means that's an exercise. Why is it the case that the Darboux aperture associated to this coarsest common refinement is upper bounded by the Darboux aperture of one of these Q's? Well, I'm just going to give you an example. I'm going to leave it to you to formalize the idea. Say I is 0, 1. Okay, I'm going to be lazy here. I'm going to take P to be the trivial partition that has exactly 1 pixel. Okay, and say Q is 0 to 1 half, 1 half to 1. Okay, let's look at this case. And I'm going to take a function. Let's say the function is like this. I'm just going to take a continuous function because they're easier to draw. So let's say something like this. That's my f. Okay. Now, if I were to look at the Darboux aperture, or maybe I should have said Q is this and P is the other one, so that it matches with this. So this is Q, this is P. So what is the Darboux aperture of Q? How do I figure that out? Well, I'm going to look at this and this. The area of this rectangle is the Darboux aperture associated to Q. Okay. Okay. But now, if I were to look at the coarsest common refinement of P and Q, well, the pixels of the coarsest common refinement is pairwise intersections. But in this case, the coarsest common refinement of P and Q is going to be P itself. Okay, I'll just write it here. In this specific case, when you take this coarsest common refinement, you get P. And so here's something like this. Now I look at the Darboux aperture of the coarsest common refinement. You see, this I cannot move, but this guy is going to go this way. And this guy, so I move up, this, move down. So you see, the area that is the Darboux aperture of the coarsest common refinement has to be less than this. Okay? This is essentially the idea behind replacing this by this. Of course, this is not a proof. The exercise is to formalize this idea, take this example, and formalize it. Okay. You essentially have finitely many pixels. To each such pixel, you sort of do this argument, and that gives you the upper bound. Okay. Any comments so far? Probably I should replace it by this by 4, by the way. Not that it matters, that specific number. OK, so I started with the Darboux aperture for P, did some stuff, upper bounded it by this guy. So if I were to take this to the other side, I have what I need on the left-hand side. So somehow, if I can control this, the difference between the upper Darboux for P and coarsest common refinement of P and Q, and likewise for the lowers, I would be done. By the way, by the exact same argument, this is always positive, and this is always positive also. When you pass over to a refinement, upper Darboux can only decrease. It cannot increase. Right? So it can only go down. And lower Darboux, when you refine, can only increase. So this is also always positive. OK. So first, I'm going to try to control this guy. For any pixel P in curly P, I'm going to define a certain subcollection of the coarsest common refinements. This is a set of intervals, so I can look at subsets of it. Define R sub P to be the pixels in the coarsest common refinements such that R is within P. Okay. Let's try to visualize what is happening here. And I'll remind you how to think of this also. I'll do it here. how do you visualize this course's common refinements? Well, the fastest way of doing this is to think of the cut points. Okay, P has a bunch of cut points, Q has a bunch of cut points. Well, you just shuffle them. Here's my interval. Same interval, and like this. Take two partitions. Say, here's P, and here's going to be Q. Okay. In the middle, I'm going to draw the coarsest common refinement. Say P is like this. Yeah, let's leave it like that. And say Q is like so. Okay, that's Q. One pixel, second pixel, third pixel, first, second, third, fourth pixel. So when you look at this intersection, some of the intersections could be empty in principle. Okay, that's okay. So what you do is, well, you just move these like this, move these like this. You don't move the cut points horizontally, okay, because that would change everything. Like this. Like so. And now, here is the coarsest common refinement of P and Q. Okay. So, I have, so we start with P. This pixel is, let's call it P1, P2, P3. Okay? And so, for each pixel, P in curly P, R sub P is going to be a collection of pixels in the coarsest common refinement. Okay? What is R sub P1? It's the pixels in the coarsest common refinement that are completely within P1. In this case, it only has this. Okay? This is the only element. So let's call these actually things and write it. So these pixels of the coarsest common refinement, I'm going to use R. Okay? R1, R2, R3, R4, R5, R6. And so curly R sub P1, curly R sub P2, curly R sub P3. In order to understand that, I'm just trying to figure this out. Collection of all pixels in the coarsest common refinement that is completely within P1. Well, this is only R1. Okay? How about this? Well, which pixels in the coarsest common refinement are completely within P2? Well, R2 and R3. And likewise, what is R sub P3? It's these three. Make sense? I guess it's an example now. This is just some sort of convenient notation you're going to see in a second. What I'm trying to do is I'm trying to control this difference. So one thing, though, that is important is that the length of pi is going to be the sum of length of rj, where rj comes from r of pi. Meaning, if I were to add the lengths of this and this, it's going to give me the length of this, for instance. Okay? You see, this is also one of the reasons why I don't like using the cut points in general, because with the indices and stuff, these kind of expressions end up becoming a nightmare to write down. Does this make sense? And certainly, if I were to take the union of all such r sub p's, as p varies in p, I'm going to get the whole coarsest common refinement. Also, well, I can just write it like this. This collection of intervals is the same thing as the union of all r sub p's. Okay, so when I'm looking at the upper Darboux sum for coarsest common refinements, instead of adding over all pixels of this, I can do double sums. And that's what I'm going to do. Leave this here. So if you look at the Taylor textbook, he doesn't really mention this mesh idea that much. He mostly uses this refinement idea. And in a sense, it is more natural, because when you think about it, if I don't use the idea of length, refinements you can just make sense of for arbitrary subsets, in a sense, or collections of subsets. So in a sense, it is more intuitive and more natural to think about refinements. But to actually use the idea of refinements in calculations, that takes a while to get accustomed to. Meshes are more intuitive for calculation purposes. OK, I'm going to continue from here. And then pass over there. So I'm trying to control this guy. Okay. Open up the definitions, write them down explicitly. Sum over all pixels of P. Height is sup of f restricted to this specific pixel times the length of the pixel. This is the definition of upper Darboux relative to P minus this guy. Oh, R. Sup, again, of f restricted to the pixel R times the length of the pixel R. Okay. Now, for each p, I'm going to replace L of p by this expression. And instead of adding over this, I'm going to add over all p's and then over all r sub p's. Okay. Continue from here. That is equal to I'll do this in multiple steps so that we see what is happening. Okay, it's like this times r in curly r sub p, length of r. Okay, I just replaced this with that. Minus, instead of having here one sum, I'm going to have two sums. One sum over all pixels in P, one sum over all pixels in R sub P. If you want, this is sort of like an iterated integral, but for summation. Okay, and I leave what's inside as is. Okay. This is a finite sum, It's a finite collection. I can take it out and consolidate the terms so that I have this. Like I said, this is a technical proof, so that's why we're doing it. Like so. Okay. Now, here's the fun part. Even though this is correct, in fact, this expression kind of overcounts by virtue of the fact that for many pixels in R, P is going to be equal to R. So look at this, for instance. In this case, for instance, P1 was equal to R1. It could happen that even though R is in P, and I'm just looking at pixels like that, if R were equal to P, then the heights would cancel. Okay? If R were equal to P, I'm just taking the sup of the same thing. And so this sum, in fact, I can take over this with the added hypothesis that R is a proper subset of P. So R is not equal to P. Okay. And now we're almost done. Any R is some interval, okay, included in some pixel in P, okay, meaning, for instance, L of R is upper bounded by the length of the pixel it is contained in, which in turn is upper bounded by the mesh of P. So this, no matter what R is upper bounded by the mesh of curly P. The difference between these two sups, well, I can upper bound it by the diameter of the image of F, independently of P and Q. Diam MF. And finally, if I think about that, how many R's like this are there in total? Well, the only way this can happen, R is a proper subset of P, is if, well, you're in a situation like this. Meaning, the only way this can happen is if there was some cut points in the other partition, Q, that sliced the original pixel in P in two. How many cut points are there in Q? If Q has, n elements, well, cut points have to be n minus 1. Each cut point in Q could contribute at most 2 new pixels. Meaning, I'm adding this constant term at most 2 times number of pixels in Q times, 2 times number of pixels on Q minus 1 times. So this is then upper bounded by this times diam M times mesh of P. But of course, instead of writing this as the upper bound, if you get rid of this minus, it's more convenient. So let's drop that minus. It's not going to matter, and this is what we wanted. This expression ultimately then upper bounds this guy. Okay. Upper bounds this. There is a very similar argument for the difference between the lowers, and that gives you Again, the same bound, again with a 2, and that's why I corrected the statement of the lemma from 2 to 4, and that finishes it. Okay? I'll leave it to you to write the bound for this explicitly, but the argument is pretty much the same. Take your time, write it slowly. And that's the end of the proof of the key lemma. It's a rather nasty sort of, it's a fun argument, but it's hard to write it out explicitly. Okay.
At what stage you change the 2 to 4?
Well, this is an upper bound for this.
Right.
I'm saying there's a similar argument that gives the same upper bound for this.
And then you add it up.
Yeah, when I add 2 of the same thing, it's going to be a 4 here.
And then number of Q and the diameter will be the same?
Exactly, yeah. Nothing else changes. Like imagine if I had, so substitute instead of U, L here, okay, to upper bound this. That corresponds to substituting all sups with infs. Okay. Keep track of this here, boom, boom. But I'm just looking at the difference between 2 infs. This is again bounded by the diameter of the image.
Can you repeat the diameter? How is it defined in what?
Yeah. This is, I'll write it again. So, this is the sup of all expressions of this form, where x1 and x2 are in I.
Previously, you also have an oscillation function.
Yes.
And you said it's inf of the sup.
Yes. The oscillation was slightly more complicated. The reason why I mentioned it was because in a previous problem set that had shown up. In problem set 4, I think, there was a question where I used this oscillation idea. I was just trying to connect diameter, the way we use it here, and oscillation. Yeah. Any other comments or questions? Okay. What do I want to do? I'll give an exercise. Now that we have this characterization theorem, I mean, part of it you're going to finish as part of problem set 6. Whenever you have a collection of functions taking real values, you always want to check if the sum is in there, scalar product is in there, product of 2 such functions is in there, and so on. And so here's part of that exercise. If you have 2 functions that are Riemann integrable on the same interval, then so is their sum. If you have 1 Riemann integrable function and 1 constant, then C times F is Riemann integrable. What else? If you have 2 functions such that one is always under the other one, then the integrals have the same property. As part of problem set 6, you're going to show that if you have a Riemann integrable function, and if you postcompose it with a continuous function, that still is Riemann integrable, just like in the case of Bourbaki integrable functions. So this is in problem set 6. By the way, probably this is the hardest part of problem set 6, actually. It's a tricky argument to get this. With Bourbaki integrals, it's significantly easier to get this. So if I were to replace r with b here, it's a lot easier than this. But you see, once I have this, what I can do is I immediately have that if f is Riemann integrable, so is its absolute value. So let's prove some statements, assuming these. So let's say perhaps observation or claim. If f is Riemann integrable, well, I'm just going to say observation, because I'm not going to write a separate proof. Say remark. Remark. If f is Riemann integrable, by choosing phi to be the absolute value function, the absolute value of f is also Riemann integrable. Okay. And using this, I also have this nice expression. The absolute value of the Riemann integral of f is upper bounded by the Riemann integral of the absolute value of f. This is, in a sense, a triangular inequality for Riemann integrals. Same thing holds for Bourbaki integrals also. What else? If f is Riemann integrable, choosing phi to be square function for phi, that is y sent to y squared, f squared is Riemann integrable. But then if I have two functions, then I can write their product in terms of squares. Right, so f plus g squared is f squared plus g squared plus 2fg, which means this is, well, f plus g squared minus plus f squared plus g squared divided by 2, I think. Well, I'll take my time. Then since f plus g squared is f squared plus 2fg plus g squared, solving for fg gives me that fg is 1/2 times f plus g squared minus f squared minus g squared. By the first item, since I'm assuming that f and g are Riemann integrable, so is their sum, and by this property, so is their square, and likewise this is Riemann integrable, and this is Riemann integrable. If I were to add and subtract whatever, bunch of Riemann integrable functions, it's still Riemann integrable, and if I scale and multiply, that's still Riemann integrable, which means that the product of two Riemann integrable functions is also Riemann integrable. Okay. But of course, just because the product of two Riemann integrable functions is Riemann integrable, you don't get to say that the Riemann integral of f times g is equal to the product of the integrals. Okay? For that, you would need something like integration by parts. But at the very least, you get to multiply two Riemann integrable functions, and the Riemann integral of the product of two functions is a valid number. Okay? I'll say this here. Warning. Of course, in these cases, Riemann integrals distribute also. Maybe I should write these as well. And Riemann integral of the sum is the sum of the Riemann integrals and so on. These are straightforward. And likewise for this, you get to take the constant out. But warning. If f and g are Riemann integrable, right, the Riemann integral of the product minus the product of the Riemann integrals need not be 0 in general. That is to say, integration does not distribute over multiplication. This is such an important thing that in probability and stuff, you would see this as correlation or variation or variance or whatever. I think this is correlation. Correlation of f and g. In probability, for instance, functions, instead of functions, you call them random variables. These are random observations you're doing. And multiplying two random variables corresponds to seeing them simultaneously, observing two separate looking things simultaneously. And the integral is the expectation or the average value. So insofar as this is 0, you would call, for instance, the random variables independent. But this is a special property. You should not expect this to be 0 in general. OK. So now I can define what a gauge is and transition to HK integrals. So we're essentially done with Riemann integrals. We're just going to modify this epsilon delta definition, if you want, just a little bit. And that's going to give us a very different, more general notion of integrability. Definition. A gauge on I is a function in the set of all functions from I into positive reals. So innocent looking of a definition, you see. A gauge is nothing but a function that takes positive values. Any function. I'm going to denote, just because I don't want to write it like this, I'm going to denote by G of I, the set of all gauges on I. OK. Now, typically we're going to denote gauges by delta because for our purposes, often we're going to replace the constant delta, in the case of, for instance, epsilon deltas, whatever, with one of these gauges. So instead of having a constant gauge, we're going to have a variable gauge. Okay, here's a nice logical exercise to convince you that we actually used gauges already. F is continuous, a function. Say on this interval, then f is continuous. Okay. Initially, what we said was for f is continuous if and only if it is continuous at any point. Well, what you can do is, instead of first fixing your point, you can use, instead of a constant delta, you can use a gauge delta. So if and only if for any epsilon, there is a delta, which is a gauge this time, not a number, such that for any x and x star in I, if the distance between x and x star is bounded by delta of x star, okay, delta is a function, so to upper bound it, I'm feeding to it a point, so now this is a number, implies that the associated images are at most epsilon apart. Okay. What it is that when I told you, as you write these logical statements and so on, you don't get to move around the quantifiers. When I said that, I was actually lying. The truth is that you do get to move them around. But as you move the quantifiers around, what might happen is that the type of the set from, or types of the sets from which you choose these variables could change. So what is happening here is that initially we had this x star here for any x star, for any epsilon. There's a delta constant and so on. You can change the orders of for alls, but if you're trying to make a for all jump over a there exists, instead of a constant, now your type for delta rises. And so instead of a constant, you have now a function that depends on x star. Okay? Now, the two distinctions, we're going to look at examples of gauges probably on Friday. But what really so there are essentially two classes of gauge functions, okay? Because I'm saying initially any function defined on I taking positive values is an admissible gauge. So this set of functions is very large. What makes or breaks things is either your gauge is bounded away from 0 or not. Hang on a minute. I think I need one more definition. Do I want to do it? Well, we'll talk about examples later. I'm going to take a sampled partition. And I'm going to take a gauge. And instead of controlling the mesh by delta, I'm going to control, again, something associated to this using this function delta. Then PS is delta fine if for any p in curly p, the pixel p is within the interval centered at the sample point minus and plus the delta. Okay. So HK integrals is going to be pretty much the same definition as Riemann integrals, the fifth item, but instead of wanting delta instead of wanting the mesh to be bounded by delta, we're going to ask our sampled partitions to be delta fine. And that's the only difference in terms of the definition. Okay? We're done for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. I'm going to take attendance today. Seven. Okay. So today, finally, we're going to transition to this more advanced type of integration, Henstock-Kurzweil integration or gauge integration. Using one of the formats of Riemann integrability, it's fairly similar to Riemann integration. We're again going to use Riemann sums, except that instead of bounding the mesh of the partition, we're going to use something called a gauge. And a gauge is going to be basically something like a bound on the mesh, but it's going to depend on the point, on the horizontal x that you're looking into. And so that kind of gives you more control as opposed to bounding the mesh. And that kind of makes all the difference. Now, I'm going to try to be as economical as possible, let's say, when it comes to these. So I'm going to give you the definitions and stuff. And then for the rest of the class, we're going to talk about some examples. Even though, from a logical point of view, it seems that it seems like everything is so innocent. It takes a while to get used to how to use these gauges as opposed to meshes. And so my plan is to next week transition to differential calculus. We're going to take a break from integral calculus. And I'm going to try to essentially start next Monday talking about derivatives. Now you're going to realize the formal account of differentiability is a lot nicer. It's not as painful as the formal interpretation or formal approach to integration. That's usually the case. Usually differentials, derivatives, all these things, it's fairly straightforward to generalize to rather bizarre contexts. But when it comes to integration, it's always mysterious. Okay. So first, I'll go through the definitions. As usual, integral calculus, my habitat is a closed and bounded interval. In other words, a compact interval, lambda to rho. A gauge on I is nothing but a function on I, taking positive values. Okay? And typically, people denote this by delta, because the point is, pretty much all other times in this course where we use a delta, for instance, continuity, whatever, now we're going to think of that delta as a function that depends on the interval. And once I define everything, I'm going to start giving you examples as well. OK. So instead of writing this longer expression, I want to think of gauges as sort of like a specialized type of functions. So I'm going to denote the collection of all gauges on I as curly G of I. If I have a sampled partition PS, so I have an interval as usual. Okay, and then I partition it into finitely many pieces, like this perhaps. And then for each of these pixels, I take one sampling point, say like so. Okay, that's my PS. And then on top of that, this we've been using so far, on top of that, I want to define a function. I want to have a function on I, right? So that's a gauge. Now I have a delta. I have an additional piece of information. Say it's a continuous function for now, so that we can draw it. Imagine delta is continuous, and it looks like this. Okay, so like this. Probably I shouldn't have drawn it like so. Maybe let's say there's like a continuous part, and then it grows like this. That's your delta. The only restriction is that the graph of delta has to be strictly above the axis, but this doesn't say anything about what the inf of delta is. Okay, the inf of delta could be 0, and we're going to see cases of that. Somehow, the fact that you can choose a gauge, depending on the context, whose inf is 0, makes all the difference. Okay, and I'll mention this here too. Heuristically, okay, as you're trying to control whatever and integrate all that stuff, heuristically, you want to engineer your delta, your gauge, so that for problematic points, delta is small. Okay? For problematic points, delta is small. If a point is not problematic, whatever that means, depending on the context, you sort of let it large, let it be large. Okay? So we're going to see specific examples of this in a second. In any event, if I have a sampled partition and a delta, I say that PS is delta-fine if this happens. What does this say? Well, for any pixel in my partition and for any point in that pixel, I want that point to be not too far away from the sampled point itself. Okay? So maybe I can try doing something like this. I'll try a different function here so that we can perhaps visualize what is happening. So for instance, here's an example for this delta-fineness. Okay. You see, there is no function I'm trying to integrate right now. Let's say my P is this. Okay, it divides into two halves. 0, 1/2, 1. That's my P. Let's say my delta, my gauge, is something like this. Okay. It's constant here. Then it drops. And there's a jump over here. Okay? This could be a delta. So now let's try to sample this partition in such a way that the sampled partition ends up being delta-fine. In fact, I'll do it like this, actually. Sorry. I don't want it at 1/2. I want it at 1/4. So this height, okay, that's the diagonal. That's 1/2. It doesn't look like 1/2. Sorry. I'll try to do it more accurately. Because, you know, underneath all the logics, it's a very sort of geometric idea, actually. That's your diagonal, like so. And I want this. Okay. This is as good as it's going to get today. I did my partition. Even though it doesn't look like it, this is 1/2. This is 1/4. Okay, and my delta is going to be this function. It's constant from 0 to 1/2. It's always 1/4. Then it drops in a linear fashion to 0. And then at 1, it jumps to 1 again. That's 1. Okay. Our aim is to sample P in such a way that PS is delta-fine. So I need to pick one point for this pixel, okay, S of P1 if you want. And this is, I'm going to need to pick one other point for this guy. So could I choose this, left endpoint for the first pixel in such a way that, so if I were to choose this, could I still say that it is delta-fine? Well, in order for this point to be allowed to be sampled, what needs to happen is, well, imagine this is your sampled point, okay? Now I need to figure out this delta. How do I do that? Well, I'm going to see where delta is at that sampling point. It's at 1/4. Then in order for this to be delta-fine, what needs to happen is that any other point in this pixel must be at most 1/4 away. But that cannot happen, you see. So the way I'm imagining this is that I have sort of this delta function. It's my gauge. I take a sampling point, okay? I'm imagining this as a firework. See, so, and then sort of drops like this, okay? So you can sort of imagine this right-angled thing, triangle, okay? So imagine sort of you look at this right triangle with two sides of equal length, okay? So in order for this sampling point to work for delta fineness, what needs to happen is this whole pixel from where this point was sampled has to be within this triangle. So if this is my delta, I cannot be sampling this specific point. I mean, I can, but then the sampled partition would not be delta fine. Okay. This is one way of thinking about this. I'm sort of imagining sort of like fireworks. It's like goes like this, and then sort of trickles down. Another way to think about it is sort of like a windshield, okay? I have my sampled point. I take the windshield. I do that. It has to be within this, the windshield, the corresponding pixel. But you see, this doesn't work. I'll write it. Not delta fine. But there is some other sampling point that I can use. Specifically, if I were to use the exact midpoint, okay? Now imagine, goes up. Again, you look at the triangle. It's completely within, you see? So the pixel from where you're sampling the point has to be completely within the base of this triangle that you draw. That's what delta fineness does. Not only for one pixel, but each of these pixels. Okay? Yeah, so you can draw triangles, you can draw half circles, whatever. It's always the same. Or if you want, you can also not draw anything, of course, if you can visualize what is happening. But as I was trying to understand what is happening here, I felt I thought it was convenient to draw something. Okay. So this is all there is to it when it comes to delta fineness. So somehow what it says is this. Once you fix your gauge delta, well, delta fineness for a sampled partition has to do with how, in a sense, representative the sampled points are for each of these pixels. So for this specific case, if you have this pixel and if you sample this point, according to this gauge delta, it says, oh, this point, this orange sample is not representative enough. That's how I'm imagining it. On the other hand, the green sample is representative enough. Okay, that's kind of how I'm imagining it. And then, of course, what we're going to do is, given the function that we're going to try to integrate, well, we're going to try to come up with a delta that sort of like finesses the bad points and good points of f. Okay. Okay, and then a gauged partition, I'm not going to use this in this class, but in the next problem set, probably you're going to see it, is a triple PS delta, where PS is a sampled partition, delta is a gauge, and PS is delta fine. Okay. So now we can define this more complicated integration. You should remember the idea for Riemann integrability, this fifth condition. F is Riemann integrable if and only if, what is it? There's an R star target integral. For any epsilon, there is a delta, okay, it's a constant, it's a number, such that for any PS in S bar, if the mesh of P is bounded by delta, implies that the associated Riemann sum is within an epsilon of the target integral. Okay? And so to get the definition for Henstock-Kurzweil, essentially all I'm going to do is I'm going to turn this into a gauge. So in the Riemann integrable case, I'm thinking of this as a constant gauge. Now I'm allowing myself non-constant gauges. Okay? So I'll write it here. For hk, replace this delta by a gauge. And we're going to have to adjust this as well accordingly. Okay? Instead of saying the mesh of P is bounded by delta, well, we're just going to replace this by delta-fineness. Replace with, I guess. I'll leave it like this. Replace by delta-fineness. If there is an R star, okay, so let f be an arbitrary function on I taking real values, then f is called Henstock-Kurzweil or gauge or Denjoy or Denjoy-Perron integrable, because technically it was Denjoy who came up with this idea first, and then like 20, 30 years later, and Perron was also, I think, independently he sort of figured it out, and then 20, 30 years later, these two mathematicians separately also defined the same integral using a much nicer sort of formalism, and we're using these people's formalism to write this out, and that's why people use this HK or Henstock-Kurzweil. That's as far as I know, this Denjoy, mathematician Denjoy, is sort of the top dog for the types of math that I'm aware of. And by the way, so that's how you read the name. You don't call him Denjoy, or Denjoy, okay, because he's French. Okay, if there is an R target for any epsilon, I don't want to say a delta constant, I want to say a delta gauge. There is a delta such that for any sampled partition, if PS is delta fine, then the associated Riemann sum is within an epsilon of R star. PS is delta fine implies that the associated Riemann sum is not more than epsilon far from R star. It's pleasantly similar to this fifth condition for Riemann integrability, as you see. Now, let's define certain classes of functions based on this HK integrability. I'll write it like this. HKI semicolon R, the collection of all HK integrable functions let's add one more. I'll write it like this. Many of the properties of HK integrability essentially work the same way as Riemann integrability. One of the things that does break, and once you learn more analysis, you get convinced that that property should break, namely that if you have an integrable function according to HK, now it is not necessarily true that for any continuous function phi, the postcomposition 2 is integrable. Okay, maybe I'll write it here. In general, if f is hk and phi is c0, then phi composed with f is not in hk. Okay? So this is a property that Bourbaki integration satisfies, that you've shown in a previous problem set, I believe, that Riemann integrability satisfies, but HK integrability does not satisfy. Okay? And seems like this is inconvenient, but technically this is something that you don't want. Whenever an integration theory allows this property, namely you have an integration theory such that if you have a function integrable with respect to it, and if you postcompose that function using a continuous function that still is integrable with respect to your theory, that actually indicates that that integration theory is not fine enough for applications. Okay? And in particular, of course, if I were to choose phi to be the absolute value function, it is not in general true that if f is hk integrable, then its absolute value is. Okay? Those hk integrable functions whose absolute values too are hk integrable are called Lebesgue integrable. And they're denoted by LIR. This is hk integrable functions such that f in absolute value 2 is hk integrable. Lebesgue integrable. Functions. Okay, so by definition, any Lebesgue integrable function is hk integrable, but not vice versa. Probably we're not going to see examples of this today, but maybe in a later problem set and so on. We'll see. Now I should mention Lebesgue integrability really is, traditionally defined through this Lebesgue paradigm that we talked about. And so even though I'm calling this the collection of Lebesgue integrable functions, there is in fact an exercise to show that this notion of Lebesgue integrability coincides with the conventional notion of Lebesgue integrability. But since we're not going to talk about this more conventional notion of Lebesgue integrability, it's not quite an exercise I can give. But for those of you who are going to take more advanced analysis classes, exercise, retrospective exercise, future or retrospective exercise. After more analysis, let's say, Lebesgue integrabilities coincide. Ints coincide. So after you take more advanced analysis classes and learn about measure theory, whatever, we can come back to this and try to verify it. But for those of you who are not going to take this more advanced class, this is clearly not an exercise that I can hold you responsible for. Okay. I should mention there are other important choices of phi, continuous functions. So if phi is this absolute value, that gives you the Lebesgue integrable functions. If you take instead pth power of absolute value, that gives you what is called LP space. That's also very useful in applications. If you use something like x log x, okay, that's a different continuous function. This now gives you what is called an Orlicz space. So, this gives you L1, this gives you LP, this gives you Orlicz. There are many others. Okay. In applications, you see, if you're trying to actually use these in the context of differential equations, whatever, now the classes of functions really matter. Okay. We're not going to be interested in these kind of things, of course. And you see this property of, oh, if I take a function that is Riemann integrable, postcompose it by whatever continuous function that is, again, Riemann integrable, that is, even though it seems like it's a nice thing, it's not. It tells you really that the integration theory is not fine enough for applications. The choice of this phi really changes what is happening underneath the hood. Okay. Is there anything else I want to define now? No. Okay. Any questions so far? Yeah.
This absolute sign means distance.
No. I'm saying take x, send it to the absolute value of x. That's a function that is continuous.
Center what?
Phi of x equals absolute value of x is a continuous function. Okay. This is C0. Its graph looks like this. If x is positive, do nothing. If x is negative, just flip it upside down.
So the definition of the back integrable function
Yes.
is that type of HK has to be C0 continuous?
No. The definition of Lebesgue integrable function is an HK integrable function such that the function in absolute value 2 is HK integrable.
You are doing composition of functions. Which
Yes.
one is doing the composition?
So this is phi composed with f for phi the absolute value function. Yeah. Right, so if I were to take this function and use it to postcompose f, this is what people write usually. Okay. Any other comments or questions? Okay. Now let's transition to examples. I want to give an example of, I want to give examples of gauges, examples of delta-fine partitions, and if time permits, I want to compute the HK integral of some function. Okay. By the way, again, by definition, since any positive number can be considered as a constant gauge, any Riemann integrable function is automatically automatically HK integrable. Maybe I should write that. Remark. Deltas are gauges. Hence, Riemann integrable functions are automatically HK integrable. And in fact, Riemann integrable functions are automatically Lebesgue integrable. Because we know if f is Riemann integrable, I mean, you're showing it as part of the problem set that is due tonight. If a function is Riemann integrable, then so is its absolute value, which means that if f is in Riemann integrable functions, then so is f in absolute value. But that means that both f and absolute value of f are HK integrable, which means that it is Lebesgue integrable. So automatically, by definition, Riemann integrability implies Lebesgue integrability, not vice versa. And Lebesgue integrability implies HK integrability, not vice versa. OK, examples. Examples of gauges. Well, constants, constant functions. So I can take an interval like this and take some constant delta. Think of it as a constant function. OK? That's a valid gauge. Any continuous function is a valid gauge. OK? So if I want, I can look at a gauge like this. OK? Or another thing perhaps would be something like this. OK? That's another possible gauge. This kind of graph really tells me, oh, this point right here is kind of like a problematic point. That's sort of the heuristic. This is where the problem is. OK? Somewhere here. OK? Now, for instance, what I can do is this. I can say, oh, if I have a delta, a gauge, that is a continuous function also, by the maximum principle, I know that it has to attain its min. But since for each x, delta of x is supposed to be positive, the inf of any such delta has to be positive also. So there's a bound as to how close you can get to 0 if you're using a continuous gauge. Inf of delta is positive by the maximum principle. But a gauge can be discontinuous, OK? And now things get really complicated. So delta with inf of delta 0. OK? These are the hardest gauges, I think, to use. So I can have something like this. OK. The inf of this delta is 0. OK. And it could have multiple discontinuities. It could be a crazy function. OK. Could be like this, for instance. X sent to 1 if x is rational, 10 to the minus 10 to the 10 if x is not rational. OK? That's a valid gauge. It's a very discontinuous function. Okay? It's not 0, you see. Its inf is bounded from below, or rather, its inf is bounded away from 0, so it would look like this. That's my delta. It keeps jumping. Okay, that's a valid function. Okay, it could be unbounded. Okay, 1 over x. I'll write that too. Here's another example. All of these yeah. So imagine this is like this, and then it's like so. That's a delta that is admissible. All of these are admissible gauges. Any comments or questions about any of these examples? Now, one thing is that when we were talking about Riemann integrability, given any number delta, there is a partition that is whose mesh is bounded by delta. You could just take the uniform partition, whatever. Now the question of, given any gauge, is there a sampled partition that is delta fine? It's slightly more subtle, okay? But ultimately, it turns out that that is something that is essentially equivalent to the nested interval property. And probably that's going to show up in the next problem set. So we did examples of gauges. Let's do examples of delta-fine partitions. Okay. Say your delta is 1, constantly 1, and you're looking at the interval 0, 1. So I is 0, 1, and delta is a function that is constantly 1. Okay, that's your gauge. Okay, like so. That's my delta. Relative to this constant gauge, in fact, any sampled partition is delta fine. Okay? Why? Because ultimately, so any PS is delta fine. Why is that? Because ultimately, I'm going to want that P is inside S of P minus 1, S of P plus 1. But I also know that the sampled point has to be in this pixel. Okay? So this, you see, is an interval of length 2. And since the sampled point is included in the partition, or in this pixel, there's only so much space you can go. So for instance, your pixel could be like this. Okay, say this is your pixel. Okay. And imagine all possible ways to sample a point. Either you're going to sample the left endpoint, or somewhere in between, or the right endpoint. But no matter how you sample it, this is an interval of length 2. It's a huge interval. Okay? So no matter how you sample your pixel, P, imagine like this whole interval of length is going to move this way. And the corresponding pixel is always going to be within. Because this has length not more than 1. ultimately this is supposed to be an interval here. Okay. Does this make sense?
Where's 2 come from?
Because this is the one side, SOP plus 1, SOP minus 1. Yeah. Okay. Let's start tightening the thing, the gauge. Here's another example. Again, I'm using 0, 1. Because as you see, I don't want to worry about lambda and rho, whatever. 0, 1 is like the unit interval. I like experimenting with it. And then here, this was delta. OK. Let's again use a delta that is constant. Say delta is 1 over 8, or 1 over 4, like we used before, somewhat. OK. So now it looks like this. OK. For this stuff, it really helps if you can draw things appropriately or according to the actual perspective. This is my gauge, OK? And so now I'm imagining this triangle business, OK? Imagine this triangle. It's right-angled. So this has the same length as this, which has the same length as this. Which means the base of this triangle has length 1 over 2, even though it doesn't look like it. Oh, yeah, that is true. Yes, sorry. This is 1 over 2. Now imagine looking at, so I'm changing the center point of this triangle. And visualize in your mind's eye moving this triangle sideways. Okay? Because the gauge delta is constant, as you're moving this triangle, it's not going to change. Okay? If delta were not constant, depending on the size of delta, the triangle would grow or shrink. Okay? And so if I have something like this, then if P is just the whole interval itself, you see, this cannot be delta-fine. Cannot be delta-fine. So there is no sampling function on P, no S on P, such that PS is delta-fine. But say I look at this, Q. Now I'm going to split it into 2 equal pieces. OK. I'll draw it like this. Now you cut it here, you cut it there, you cut it there. Now for this Q, it's another partition. For some sampling functions, QS or QT is not delta-fine, but for some, it is. Right? So for instance, if I were to use T, let's call this the first pixel, Q1, Q2. I need to sample 2 points. Say for Q1 I sample 0, and for Q2 I sample 3 over 4. This is a sampled partition now. Okay? But this is not delta-fine. Why? Because the sampled point for the first pixel is this. But according to my gauge, you see, I look at the triangle, the corresponding pixel is not within the base. This is not delta-fine. Not delta-fine. Okay. But for instance, if I were to do 1/4 and 3/4, let's call it STU, sample the midpoints, 1/4, 3/4. Now Q comma U again is a sampled partition, but you see this time okay, you're sampling the midpoints. Take this triangle, imagine its center to be here. See, you exactly see this. And likewise, you exactly see this. So this is delta-fine. Make sense? Yeah.
So if you sample at T0, it's not delta-fine.
Exactly.
Because what?
Because of this specific, so delta is a specific gauge. What needs to happen is you have your sampled point. I'll write it here. So because for delta-fineness, need what? I need that Q1 is within delta of its sampled points, meaning Q1 is a subset of 0 minus delta is 1/4, 0 plus delta, plus 1/4. But this doesn't hold. That is a condition for delta-fineness. When you sample a point from a pixel, that pixel has to be close enough to that sample. And how close enough? The gauge tells you how close enough. It does take some experimentation. So in a sense, the way I'm imagining this is that before, we didn't really care that much about what the sampling function was. Okay? We only needed it to write down the Riemann sum. But now, we have this extra condition that the sampled point for each pixel is representative enough. Okay? If I have this pixel, and if I sample this, that's not representative enough. I look at the triangle, the corresponding pixel is not within. But if I were to choose the midpoint, as I do here with you, now the midpoint, according to this gauge, is representative. Too many moving parts, I realize.
So if I rephrase it, you pick a sampling point.
Yes.
And then you look at the partition.
Exactly.
Maybe.
Yeah. I mean, you're right. We're sort of like reversing the way we think about things. You're right. Okay. That's it for today. I want to give more examples. I think that's what I'm going to do on Monday, but we're done for today. Thank you.